has any. We did section 8.4 last time, so if you guys have any additional questions about things or homework questions or anything like that, I'd be happy to take some time now and do those. If you don't, that's no big deal. Just kind of giving you the option. Okie dokie. Again, I think 8.4 is relatively straightforward. If that, if that changes or whatever, you're always welcome to kind of go back and we can ask more questions later. I imagine some of us were caught off guard and didn't have everything we needed to do, to work on things when there's a snow day that, and all that. So no big deal. Again, that's the beauty of having the homework check always that Sunday weekend, right? Is that if something happens or get behind or whatever, that's not a big deal. Or there's some flexibility there. Okay, so we're gonna kind of move ahead here, and we're gonna start talking about, or continue talking about vectors here. We're going to, though, now extend this and start talking about three-dimensional situations. But before we can talk about a three-dimensional vector, we really need to talk about, like, the three-dimensional coordinate system. So there's a couple of different ways you could represent that. Typically, when we do that, we're going to represent it with like the right-handed version of this. I think even, yeah, boom. OneNote has a 3D coordinate system kind of built into it. So when we do this, you have to look at this like with a little bit of perspective, and that dashed line, you need to kind of look at it as if it's coming out of the board towards you. So you have to look at it with like a three-dimensional perspective. So like the XY plane is the plane that's like coming out of the sheet of paper, right? Okay, let's try this instead. I see some confused looks. Take a look at the corner, like a corner of the room. Any corner, on the ground or in the ceiling or whatever. Probably the ground is easier. And you have like that the corner of the floors meet at a corner like this. And then the wall continues kind of straight up, right? So the up and down axis we call the z-axis, and then the two axes that are in the plane we call the x and y axis. So this is really the same part as like that. Does that help kind of get the 3D perspective there a little bit more? Again, if you get stuck on that, it just try to attach it to like a physical part of the world. It's a lot easier to look at a corner and kind of imagine the axes than it is maybe necessarily to just look at the flat axis on a sheet of paper and try to imagine the three-dimensionalness of it. It takes a little bit of imagination to kind of see that. But it's not so bad. So when we do this, this is the positive end of the y-axis. This is the negative end. This is the positive end of the x-axis. This is the negative end. That's the positive end of the z-axis. That's the negative end. So let's do an example where we just graph a point. So keep in mind, when we describe a point in 3 dimensions, we need 3 components for that point. So we're going to give you this ordered tuple here. So the components are, we write typically in alphabetical order. That's the convention. So the x component is first, the y component is second, the z component is third. That is the way that I will always write it. That's the way that you should always write it. That is the convention. Please don't write them in a different order. Okay. All right. So to graph a point in 3 dimensions, it's a little bit tricky. It's not quite as easy as graphing something in 2 dimensions was. But I'm going to start by putting some tick marks on my axes. So on the positive x-axis, I'm going to put in like 3 tick marks. On the positive end of the y-axis, I'm going to put on 2 tick marks. And at the positive end of the z-axis, I'm going to put on 5 tick marks. Everybody okay with that idea? Okay. So what I'm going to do now is it doesn't really matter which one you do. I like to start with x though. From x equals 3, I'm going to draw a line that's parallel to the y-axis. And then from y equals 2, I'm going to draw a line that's parallel to the x-axis. And find that intersection, which is right about there. Okay with that? Again, like we're eyeballing, so if yours is in a little bit different location, that's okay. It shouldn't be exactly on the z-axis though. And then I'm going to draw a line parallel to the z-axis up to z equals 5. Oh, I'm sorry, that's not right. That's not right. Sorry, let me just undo a lot of that. That's not how I want to do that. Okay. Sorry, I don't want to do that. Okay, so this makes like the bottom, or makes like a, well, it's a rectangle, but it's drawn with perspective, so it doesn't look rectangular to us. But it is rectangular because those are all like intersections of axes or things that are parallel to axes, so they have to be at right angles. Everybody's okay with that, even though it doesn't look like they're right angles, we know they actually are. It's the perspective that's throwing it. Those of you that are art students, that should feel okay, right? Okay, so what I'm going to do now is I'm going to draw up to here, and I'm going to draw up here and kind of make a box here. So like what I've done is I've gone 3 on the x, 2 in the y, and then 5 up the z. And this is my point that I care about here. So you see how when I found the intersection of the x and y, it was like the front of the box? I'm going to then just travel up the z-axis, so I want that front right corner of the box is where my point is going to be. Let's do another, just to kind of make it maybe a little less choppy, kind of going through it. Again, it takes a little bit of like imagination, thinking about it in 3 dimensions. But once you've got it, it's not too bad. Okay, so X, Y, Z. So we're going to go 2 tick marks on the positive X, 3 tick marks on the negative Y, and then 4 tick marks up the positive Z. I'll draw my line that's at X equals 2. And I'm going to draw that so it's parallel to the y-axis. We're trying to be anyways. And then from y equals negative 3, I'll draw my line that's parallel to the x-axis. So there's like the bottom of my box. So now I'll draw it up to the z-axis. To complete my box. And there's my point, since the point on the base was at the bottom or the front left-hand side. That's what I want. How many of us have done the art class where you do the perspective drawings? Few of us, maybe? This should feel kind of similar to things that you would have done, like from an art standpoint, and drawing your perspective drawing and getting things scaled correctly. This should feel a little bit familiar. If you haven't, it's not a terribly difficult process, but it's something different and kind of new. And if it doesn't feel great, that's okay. You'll have a chance to practice in the homework, and it's one of those things like once you got it, it starts to make sense because things look nice. Do we feel a bit better about that after the second example? A little less choppy that time. I stumbled over my tongue a little bit less there. Let's give a couple of definitions. So in 3 dimensions, we still want to be able to talk about the distance between 2 points. So in 2 dimensions, the distance formula was the square root of like x1 minus x2 quantity squared plus y1 minus y2 quantity squared. You guys remember that from like algebra or geometry? So if we add a third component, how does that change the distance formula? Well, we just have a third component in the distance formula. No big deal. Everybody's okay with that? That should feel like a natural extension. That's probably what we would hope for, right? Is it's just the same formula, just slightly modified. Similarly, we'd like to be able to find the midpoint between 2 points. So if you remember back to Algebra 1 or geometry, to find the midpoint in 2 dimensions, you basically did x1 plus x2 divided by 2 and y1 plus y2 divided by 2. Similar idea here, except now we have a third component. So just a quick numeric example using these 2 formulas. So my distance is going to be 6 minus negative 8 minus 5 squared plus negative 2 minus 11 squared, all square rooted. Now remember, it doesn't really matter which one we're calling, which point is x1, y1, z1, and which point is x2, y2, z2. It's pretty arbitrary. So I just usually, whichever point is the first one, I start as the x1, y1, z1. The second point is x2, y2, z2, just because it's less likely for me to like start interchanging the coordinates, which is bad, right? That's the one thing you can't do, right? Whatever's point has the x1, it also has to have y1 and z1. You can't have x1 from this one, y1 from that one. But you guys know that, right? Anyway, so I plug that into my calculator and I get the square root of 534, which if you type that in, which is approximately 23.11. Then similarly, the midpoint is going to be 6 plus negative 8 divided by 2, negative 8 plus 5 divided by 2, and then negative 2 plus 11 divided by 2. And when I simplify those, I get negative 1, negative 3 over 2, and then positive 9 over 2. Again, you could turn those fractions into decimals, but I'm not going to bother with it since a reduced fraction is just as good as a decimal. Not wrong if you wanted to do that. You guys feel okay here? Good, that was the end of 8.5. I know. Wasn't a lot to do, but like that was necessary stuff. By far the hardest thing to do is drawing the points, right? So the rest of it, though, should have been pretty easy. Today we're going to continue on. We're going to talk about 3D vectors. And again, you're going to find that for the most part, everything that we did in 2 dimensions has a natural analog to 3 dimensions. So not going to be anything tremendously different. So I'm just going to make like I'm going to just kind of do it this way. And I'm just going to make a little table comparing and contrasting the two things because they're basically the same definition for most of these things. And it gives me a chance to review some of the vocab. Let's actually save that. So component form in 2D was the wedge notation. So we have the vector AB. If we have a three-dimensional vector, that's vector ABC. We have the IB component form notation, which is the column vector AB. In 3 dimensions, it becomes the column vector ABC. So the magnitude the head minus tail rule is still the same. So that's just how to take, again, a vector into component form. And component form is preferable, again, because vector addition is much easier to deal with. So we have linear combination form. This was something else. That was another way to represent our vector. Where the J, and then in the 3D case, K are our unit, or standard unit vectors, I guess I should say. If I add two vectors together, we just add their in 3 dimensions. All that means is that we're have a third component that we have to add. All of this should feel pretty nice, right? Nothing is really different. You're just, everything's working the exact same way. You just have like an extra component to deal with, which has been pretty trivial. So there's the vector additive inverse. Which was just the negation of the components. So in 3 dimensions, I have 2 commas there. Same idea. And really that's just a special case for scalar multiplication. And the last vector operation we had was the dot product. So again, with third dimension, there's just like a third product that you make by adding or multiplying the z components together and then adding them. Okay. And then all the dot product properties obviously are still going to hold in 3 dimensions. So like u dot v is the same as v dot u. U dot 0 is just 0, or sorry, u dot the 0 vector is the number 0, I should say. Be a little bit more clear. The distributive property, the scalar associative, the magnitude property, all of those things still hold. Okay, so let's do a couple of numeric examples here, or a numeric example, I guess. So the first thing I would do is I would just convert this vector that's in the unit vector form into component form. Gracie? Yes, of course. And then I know that this, I can just multiply everything in u by 2 and then add it to v. Which gives me -4, +3, and then +2, and then +5. Right? -4 plus 7 is 3, 8 minus 6 is 2, and 14 minus 9 is 5. So far, so good? Now, to graph this vector w, we're going to kind of do it the same way we would in 2 dimensions. So we'll start by graphing the point 3, 2, 5, and then we'll draw the line from the origin to that point. Everybody's okay with that plan? So I have to graph the 3D point 3, 2, 5. So again, this is the x, y, and z. So 3 on the positive x-axis, so 1, 2, 3. 2 on the positive y-axis, 1, 2. 5 on the positive z-axis, 1, 2, 3, 4, 5. So parallel to y, parallel to x. Draw the base of my box here. And I always go to the piece that's at the z-axis and y-axis. That's going to give me my roof. Then I'll draw my line that's parallel to this piece down here. It's about the same length. Similarly here. So like that is the location of my point. So to draw my vector then, I'm going to start at the origin and draw the head to that point. I get too messy? I can try to do it again where it's a little bit neater. Ooh, this turned blue. That's neat. I didn't know that was going to happen. Ah! Okay. Try this again. I tried making things a little bigger. I figured that would make it easier to be neat. You know what I mean, guys? So far, so good. I didn't quite get that piece parallel there, though, huh? It's hard to draw neatly on the tablet. Those of you that are tablet users can feel that, know that pain there. Yeah. So there's my point. So there's my vector going from the origin to that point. Does that help at all? Trying it again, trying to be a little bit neater. Hopefully it did. All right, so the last thing I want to talk about today is going to be 3D vector equations of lines. So one thing that we'll notice here in this, that we'll get to in the next section, that you can't describe a equation for a line in 3 dimensions using just x, y, and z. An equation in 3 dimensions with x, y, and z in it is going to actually describe a plane and not a specific line. So this is a situation where a vector equation of a line makes a heck of a lot more sense than trying to draw or trying to give a linear description of a line with 3 variables, because you can't write one that way. So just like before, to write the equation for a line, we need a point and a slope. But again, we're in 3-dimensional space, so slope doesn't really make sense in a 3-dimensional space because you have 3 components and not 2, so there's no rise over run in 3 dimensions. Is everybody okay with that idea? So what we really think about, instead of using slope, remember slope was just a proxy for direction for the line, was describing that tilt. We're going to use a direction vector similar to what we did in 2 dimensions to kind of describe that tilt. It'll be a little bit different the way we find that direction vector, but it's going to kind of make the same idea. So the way we define our equation for the line is exactly the same. So like given a point P naught on the line R, and a vector V naught passing through, I should say a vector, and also another vector V in the same direction as the line R. The equation of R can be given as this was supposed to be an R naught, excuse me, not a V naught. So let's look at an example. Okay, so let's say we want to find a possible vector line equation that passes through the points 5, -2, 6, and -3, 4, 1. Note I said possible here because just like for vector line equations in 2 dimensions, there's going to be lots of possible answers. All right. So we should pick one of these to be kind of like our initial points. So it doesn't matter which point. I'm just going to do the first one. that means that, well, I can choose my vector R0 that just needs to pass through that point P just to be the component form of that point, right? Remember, that is describing the vector whose tail is the origin and whose head is that point 5, negative 2, 6. So that certainly is going to pass through the point 5, negative 2, 6. Everybody okay with that? And then for my vector R, I just need it to be in the same my vector V, I just need to be in the same direction as the line R. So the easiest way to do that is just to find the vector that passes through these 2 points, or the component form for the vector. Oh, shoot. Well, I guess it doesn't really matter, does it? Let me think for a moment. Yes, that does matter. I'm sorry. Let me point. I have to fix that. Okay. So good thing I made this mistake here, because it gives me an opportunity to mention it to you guys, because it's an easy mistake to make because I just made it. So if I need to pass through point P0, that needs to be the head of the vector P naught, right? Oh, I'm stupid. It didn't matter. No, it doesn't matter. I got all excited like it was going to matter. It didn't matter. My apologies. Whether you did the first point minus the second point or the second point minus the first point there, to find your vector V doesn't matter. I lied. So there's like 4 combinations of answers that you could get, right? Using the first point as P1, and then whichever way you did the subtraction to get V. And then the other 2 would be the second point as P naught, and then either way of doing the subtraction to get V. So there's like 4 possible answers here. I don't want to write all 4 of them down because I'm lazy. Do you guys get what I mean when there's like 4 pretty common, easy to get to answers there? Does it matter which one you give me? No. They're all equivalent. Okay. We're doing great. Okay. So here we're asked to determine if the point -5, 6, 11 is on the line the vector r equals -3, 12, 7 plus 1, 3, -2t. So basically what we want to see is if I can solve this for t and get the same result. So this really becomes, when I do my scalar multiplication and vector addition over on the right-hand side, this, and I'm going to show a lot of work here that isn't really necessary for you to show if you're doing this problem, but I want to make sure that it's clear kind of what I'm doing. Oops, that's not supposed to be, that's supposed to be equal sign. So if those two things are equal, then system has to have a solution so if I solve this system for t, I get -2. And if I plug that answer back in here, 12 plus 3 times, 12 plus 3 times -2 is 6. So that equation is satisfied with the solution for t. And 7 minus 2 times -2 is 7 plus 4, which is 11. So it satisfies the second equation. So the answer is yes, that point does lie on that line. If it wasn't the case, when you tried to plug that answer for t back into the other places, you would have had at least one of the components that wouldn't have been equal. Ben? Well, I solved. So I added 3 to both sides to solve that first equation, because there's only one variable in it, to see if they satisfy the next two. Yep. Correct. And it has to work for both, right? Your answer for t has to satisfy all the equations for it to be yes. Yep, that's the idea. Again, not too terribly difficult here. And let's stop. That's 3 sections we've done today. The last section is by far the most complicated one, so let's leave that to have a day on its own. Because, well, we can afford to do that. So let's see here. I don't know if you guys noticed, but I did put 8.4 homework problems on Power School. I don't know that I think with the homework quiz, I probably forgot to write them down for you guys. That was from last time. Yes. So this stuff will be for Sunday's homework check. Whatever we do on Friday would be on next Sunday. And you guys should take all of our remaining time and kind of start on things. I know this was a lot of stuff to feel like it just got dumped on you. My apologies if it feels that way. It wasn't really my intention. It's just kind of the way it worked out. And if on Friday it feels like this is impossible, we can reassess or whatever, okay? I don't want it to feel like you just got, 100 problems dumped on you when you weren't expecting it on a Wednesday, asking it to be due on Sunday. If that feels unrealistic come Friday, we can reassess, okay? but I think for the most part, the problems are fairly easy. I know there's a lot of them, but none of them are terribly complicated or require a lot to do. But if that still feels unrealistic, we can talk again. Okay?